So we've got one more idea that to cover in chapter 19, and it's much simpler, much smaller of an idea, but it has to do with choosing the correct sample size, as it says there on the screen. And basically, what we're talking about is, in order to hit a particular level of confidence, or I'm sorry, not a level of confidence, but to have a certain margin of error, because sometimes you're going to go into collecting data thinking, I want to be pretty certain. I want this to be a pretty small margin of error or pretty big, whatever it might be. So there are times where you have an idea that I want this to be my margin of error. And while you have some control over the confidence level, really the only thing you can manipulate is the sample size. And you want to make sure you want to have a sample size big enough to result in the margin of error that you're looking for. That's why a lot of times when you see sampling information, it's not 100 people were surveyed, or 200, or 1,000, or nice neat numbers. It was 1,017 or something like that. There's these numbers that are quote unquote weird because that was the probably the minimum size needed in order to correctly to hit that margin of error. So it's really just a lot of math that we have to concern ourselves with, and it only involves the margin of error formula, which is from before. The margin of error is the critical value, z to the asterisk, times the standard error, which is the square root of p hat times q hat, all divided by n. And that's just a reminder. This is what they're telling us. This is how many. Uh, this is a standard deviation, and this is how many standard deviations we need to go above and below the sample mean to hit our level of confidence. So that's where we start, and we want to figure out what n has to be. So it's really just a lot of algebra. I mean, first thing first, we want to remember that when you're finding the square root of something, it's really the same as the square root of the numerator divided by the square root of the denominator. But hopefully you're not having too many flashbacks about algebra as we proceed here. We got to get that square root of n out of the denominator, so we're going to multiply both sides by n, a square root of n, that is. And you can kind of see where this is going. And we're going to then divide both sides by the margin of error, and then square root everything, and to get rid of the radical sign with the n, and we'll have, so if you need to find n for a given margin of error, for a desired margin of error, I guess, you take the critical value squared times p hat and q hat, and then divide it by the desired margin of error squared. Couple things to note. You should always write the margin of error as a decimal. Don't write it as, I want it to be 3%, so throw 3 in there. Write it as 0.03. That's important. And this one right here can be problematic. If we're choosing the correct sample size, it stands to reason that we don't have any sample yet. We haven't collected any data because we don't know how many people we have to ask. So would probably be one of the first things you have to do before you actually collect any data, is figure out how much data you need to collect. So this idea of having a P hat and a Q hat are probably, you might not have it. So you have a couple of options here, because this is not exactly hard and fast science in the sense of it's kind of, if you're going to make a mistake, you're going to make a mistake going over. And if you have something that would give you a reasonable estimate as to what the sample proportion would be, you can use that, right? If you're collecting information about a politician's favorability rate or something, and it works that that it was previously 61%, you could probably use 0.61 for your p hat in this formula, given that it probably hasn't changed all that much, barring some sort of political disaster. Um, but if you don't have anything on which you could get an estimate for p hat and q hat, you use 0.5 for both. Make it a coin toss, right? And that way, that's as big as you can make that in there, right? That's as big as you can make that, because uh, everything else is going to be less, right? So if you don't have anything on which you can get an estimate for p hat or q hat, that will use 50-50, right? And if the question's asked of that in any situation, normally they'll give you like backstory that may or may not seem necessary. That's why it's necessary. That's what they're giving you, right? And always round up. This is a situation where you're talking about how many people you need to distribute a survey to. So you're not going to give half a survey. You're not going to give a quarter of a survey. You have to give all of it, right? So that's really the last idea that we talked, that chapter 19 has it beyond the confidence interval. The confidence interval is the big one, right? And all the things that we could pull from that, i.e. margin of error, critical values, what is it telling us? How likely is it that something is actually that, all that stuff. But this is the other kind of process that you might need to do in order to in order to create that desired margin of error. All right. So that's it. That's a quick little lecture about choosing the correct sample size. And I don't know that there's a ton of practice in the book, but they work it in on some of the multi-step ones. I think it's oftentimes part B or something like that. So get some practice on that. And again, it's really just a procedure thing. This isn't in the formula sheet, so there's an element of this is the margin of error formula is to a degree, but the algebra that we have to do here, and it's straight algebra, there's nothing purely statistical about this, isn't. So you'll have to remember how to do the algebra. Right? So please let me know if you have any questions. I hope this helped.